Hello guys, welcome back to my channel, Tekken Boy. It is another Simulkuy episode, and in this episode I will be talking about reaction, and this time it's about reactor tuning. So how if your reactor don't get the conversion that you want, what should you do? And yeah, that's basically what I will discuss in this video. So yeah, in this episode I will be using uh, an H3 or ammonia synthesis reactor. So let me show quickly about the components and the fluid package and also the reaction sets. Okay, so here I have some components such as methane, H2O, CO, CO2, H2, N2, O2, ammonia, and argon. And for the fluid package, I'm using the classic Pang Robinson, yeah, without any change. Um, And then for the reaction set, actually we don't use all of this, yeah, because uh I crop it from the complete simulation, so there are a lot of reaction sets, but actually what will we use is only one kinetic and one equilibrium reaction. For the kinetic, we will use this synthesis one reaction set. Yeah, so the reaction is between the nitrogen, then hydrogen become ammonia. Yeah, and for the kinetic parameters, this is what I use from my reference. And then for the equilibrium, we're using this set. Yeah, so I just need to put the component and also the coefficient of stoichiometry. All right, so I will return back to the simulation environment. Yeah, before we start to tune this reactor, um, I will refresh a bit about what is actually affecting the conversion of the reaction. Okay, so first we have the volume of the reactor. Yeah, because if we have more volume, it means that we have more residence time. Yeah, if we have more residence time, it means there are more probability for the components to collide and to react each other. So it will make the conversion higher. And then the second one is fit rate. Yeah, of course, because this is also related with the residence time, right? Because residence time have the correlation between the fit rate and also the volume of the reactor. So for the fit rate, because if you have less fit rate, it means that with the same volume of reactor, we will have more residence time. Okay, so the reaction or the conversion will be higher. And the third one is the kinetic parameters, yeah, because this is a kinetic reactor, so it means that the kinetic parameters will affect the conversion. It will affect by showing how fast the reaction will reach the equilibrium. So definitely kinetic parameters will be affecting the conversion of the kinetic reactor. And then the fourth one is the operating condition. Yeah, temperature and also pressure. For temperature, because we know kinetic also depends on the temperature, and this operating condition will also affect the equilibrium conversion. Yeah, because if we change the condition of operating condition, the equilibrium will shift also. And then lastly, it's about the fit composition, because the fit composition will affects the molar concentration and also the partial pressure. Yeah, because this two parameter will affects the reaction rate. Yeah, because if we see here in our reaction rate, yeah, we have the forward order of nitrogen and hydrogen. So in other words, if we have more concentrated nitrogen and hydrogen, it will increase the rate of the reaction. Okay, so we will try some of these parameters. Yeah, the first one is the volume, fit rate. Also, we can try kinetic parameter. We can try, and operation condition. Also, we can try composition. Also, we can try. Okay, so first of all, we have this feed, yeah, at 200 Celsius, at 150 bar with the molar flow of 14 Okay, this is my composition. Yeah, you could take a screenshot and do it in your case file. And for my reactor, this is my starting point. So I put the delta P of 15 kPa, and then the reaction set. Yeah, I use the synthesis one. Number of segment 5. I leave it as default for the catalyst data uh, with the void fraction of zero point 0.5. Length, diameter, number of tube, wall thickness, yeah, as displayed. So this is the starting point. And if you see uh, the conversion is very low. It's only 0.26%. So if we look at the composition here, our ammonia generation is still very low because actually in the real ammonia converter, the conversion of NH3 will be done in several steps, or in several bed. In the first bed, uh, usually it's not this slow, and the conversion, yeah, also not this slow. So definitely we should work to increase the conversion. So first of all, before we start tune the reactor, I will display first the conversion here. So we can always observe the conversion value each when we variate the parameters. Okay. The second step is before we jump into the kinetic reactor, I will use first the non-kinetic reactor. And in this case, I will try to use the equilibrium reactor. Okay. Why? Because I want to know what is the equilibrium conversion in this condition, because I should expect that the PFR will not exceeding the equilibrium conversion. So yeah, that's the first objective, and the second objective is to really make sure that the reaction work. Yeah, because if our reaction not working in the conversion, you don't expect it will work also in the PFR. Yeah. Okay, so I will use the same feed, multiple connection. Okay, let me do it real quick like this and attach the reaction set. Okay, so my product will be in the vapor space. Okay, so now we can see the conversion here is 31.66. So it means that yeah, my reaction in this condition is uh, okay already. It's already resulting in some conversion. 30 is a good conversion. So I can expect that my PFR actually able to get this close of conversion. Yeah, but in reality now it is 0.26%. So if you have this condition, definitely you should tune the reactor. Okay, now let's go to the first factor is the reactor volume. So from the rating, right now the current length and diameter is 1 for each. We can try to vary the length, yeah, for example, to 6. Yeah, you could see that the conversion is already increasing to 0.54. If I increase to 8, yeah, it will jump to 25%, which is quite close to our equilibrium conversion. So yeah, I will go back to 1. And for the diameter, yeah, we can also definitely change this, for example, to 2.5. It will go to 2.76%. It's still quite low, but it's increasing. If I increase to 2.8, it will be in 25.63. So yeah, this is the quite same conversion from what we get with the length of 8. This is, I can say, the maximum conversion that we can get, because if we increase the length, you could see that it will not really affecting the conversion. So yeah, I will pick this sizing. But if you want to have the reactor uh, has more length than the diameter. So you can use the previous one. You put the length at 8 while the diameter stay at 1. So you also could see that the effect of diameter will be larger, yeah, because in a lower increment of diameter, it will have more impact in conversion. It's very obvious because if we want to calculate the volume, diameter have the square on it. So the effect will be quadratic while length is have no square on it. It's a linear correlation with the volume. So yeah, we could expect that the diameter has more effect to the volume and more effect to the conversion. Okay, so that's the first. I will go back to the early numbers to 1%, sorry, to 1 meter. So now we will try to change the second factor, which is the feed rate. So for example, I will lower my feed rate to 1E4. So you could see that the conversion will increase, okay, from 0.26 to 0.38. Yeah. If you think that the dimension of the reactor is already big enough and your reaction kinetic is already correct, then you might think whether your feed rate is actually makes sense or not. Because if the feed rate is too high, it means that you need a big volume of reactor. So yeah, for example, if I increase further this to E4, you could see that the conversion will be more lower. So you could see also that the equilibrium reactor not change the conversion of the equilibrium reactor not change, yeah, because it is not really affected by the flow rate of the feed. The effect is more to the composition of the feed and also the operating condition of the reactor. Next, the third one is about the kinetic parameter. So what you can try is you go to the reaction view and then go to the active list. So yeah, this parameter. You could see the equation, right? Because R is equal to K time F basis. So it means that if you have higher K, it will increase your reaction rate. So for example, if I increase this A, um, yeah, A is linear to the K. So if I increase A, it will increase also the K, right? I increase to 15,000. Yeah, you could see that conversion is higher. Okay. Now for the E, term, because it is in the minus exponential. So if you want to make the conversion higher, you should lower your E. For example, I lower to 60K. Yeah, you could see the conversion become uh, very high, 54%. Yeah, but you need to tune this accordingly, because having more conversion doesn't mean that it is always a correct one. Yeah, because I think this is not really makes sense, yeah, to get 50% conversion for this condition. So yeah, you need to tune this uh, logically. Why the E have more effect? Yeah, because it is in the exponential term of the K. So if I change a bit, it will have more effect to the K. Okay, now the next thing is about the operating condition. So if we have the feed at 200, we can alter this temperature. Yeah, we could also see the effect to the equilibrium reactor, because equilibrium will depends on this operating conditions. For example, if I increase to 50, yeah, you could see that we have lower in the actual conversion become 27, but we have increase in the reactor conversion. Why? Yeah, because if we increase the temperature, it will increase our kinetic rate. But in this condition, if we increase the temperature, it will shift the conversion to a lower conversion, equilibrium conversion. Okay, so if we see in the point of view of equilibrium conversion, it will get lower, but our reactor could have more conversion because of a higher temperature. So this is like the balance between you have the fast reaction with the high equilibrium conversion. So yeah, this is something that you can tune and you can decide for your process design. So yeah, I will get it back to 200. Now I try to increase or decrease my pressure. For example, I want to make it into 1E4. Yeah, you could see I get less conversion and also less equilibrium conversion. You could see that I get less PFR conversion and also less equilibrium conversion. Okay, so if I have more pressure here, it will increase both my conversion, yeah, PFR and also equilibrium conversion. The last thing is about the feed composition. Yeah, for example, in this case, I have argon and also methane, which is not really used in this reaction. It is acting like an inert. So, for example, if I change this composition, it will affect my PFR conversion and also the equilibrium. Okay, I will put, for example, the methane and also the argon into 0, so I don't have any inert that I will normalize. So you can see that the fraction of the hydrogen will be increased. Okay, I click OK. I will get the lower equilibrium conversion. Now, if I go back for example, 0.1, argon, I think it's too high, 0.01. 0.01, normalize. Okay, you could see that in the terms of kinetic, you get more conversion if you have a concentrated feed. But in terms of equilibrium conversion, it is not always like that. So be careful on this. Because in the kinetic terms, if you have more concentration, it means that the basis or like the molar concentration or the partial pressure will increase. So definitely it will increase the reaction rate. But in terms of equilibrium conversion, it is not always like that. Okay, so that's all that I can deliver about reactor tuning. We able to demonstrate all of these 5 factors that affect the reaction coefficient. Okay, so that's all for this video. I hope this will be useful for you, and see you in the next Simulkuy episode. Bye bye.